Okay, first of all, thank you very much for giving me the opportunity to be here a second time after last year, the presentation. And yes, I want to present the current state of a European project which is called NanoMar, and it is dealing with the MRI-based navigation and control of micro and nanobots to achieve targeted drug delivery, in contrast to conventional approaches. This? Oh. Okay, so first some things about the topics what I'm going to talk about. First of all, I will present the concept of the MRI-controlled targeted drug delivery. I will say something to the multidisciplinarity of this approach because it involves much input from many different disciplines. I will talk about the MRI-based tracking and propulsion of the capsules. Then one core topic is the analysis of the MRI artifacts which are produced due to the imaging of these small ferromagnetic particles. Then I will say something to the design of these capsules and nanoparticles and give a short report on ongoing developments and the achievements what we did and the demonstration scenarios which we are going to test it in. So first of all, targeted local drug delivery means we have a tumor here and we diagnose it, and then we just inject some functionalized particles, functionalized nanobots or microbots into the cardiovascular system, and then we make them gather around the tumor and directly target the tumor. So that is how it's done already in some cases. But in our case, we want to inject them and stay together like a group. And then we control them in a very deterministic way to move them to the place where they should work. So there are a few challenges concerning this work. First of all, we have to improve our imaging to be able to image to diagnose the cancer tumor and to image the particles to be able to control them. Then we have to somehow make them go to the right place so that they can work. And then, of course, these particles have to kill the cancer cells in some way. So, and the project NanoMar aims at developing a system to do drug delivery near the tumor. That means we use the MRI as not only as an imaging system, but also as a propulsion means. So we use the magnetic gradients produced by the imaging coils to push the particles in the direction where we want it to be. So we use enhanced diagnostics using the MRI. We're working on that. We use the in vivo propulsion and navigation of the particles, and we use nanobots to target the tumor with drugs. So there are quite some different disciplines involved in this. First of all, of course, we have the system and the hardware. So we have modifications to the MRI system, which should be constrained to software, not too much hardware changes due to regulation problems then. Then we have the nanocapsule fabrication. We have to produce them. We have to make them work in the way like we want them to. And we have to either develop or take drugs and functionalize these nanocapsules with the drugs. Then we have to use simulation, first of all, for the nanocapsule fabrication to make sure that the fabrication works. And of course also to validate that our approach of propulsion and imaging is valid. And then of course the biological side, so materials, what we have to use, the biological effects, what we are going to exploit using the nanoparticles. So how we are going to do that? We have to implement 3 essential components which we need for the navigation of these untethered nanobots in the human body. First of all, we need propulsion. So we use the 3 imaging coils of the MRI system to push the particles. And that means we have to control the MRI in that way that the gradients are switched in that way so that we move it. Then we have to track and locate the particles using the standard hardware of the MRI and additional software. And we have to control it. So that means combine the information what we got from the tracking and the possibilities what we have about propulsion to control it in the way that we want it to move. So in this, on the right, there is the system approach what we have. So we have the MRI system with the nanocapsules somewhere in the body. Then we do image generation. So we extract images of the area surrounding the particles. We do image processing and extract the position of the particles, of the nanobots or microbots. And then this gets transferred to a controller which will decide where the nanobots should go according to pre-existing data on the cardiovascular system and the path what we have to take. And then this controller decides directions and paths and programs a low-level controller which will switch and decide and design the gradients to do that. And of course a user interface so that everything can be controlled by a doctor. So in order to see where the nanobots are, we have to image them due to the fact that these nanobots are ferromagnetic material, so that we can push them using the gradient coils. We are getting very strong artifacts and very big artifacts in the images, scaling much greater than the size of the particle itself. So we simulated these artifacts for certain small particles, and we validated that in experiments. The goal is we want to quantify how big the artifacts are, to understand the process of artifact formation, and then to conclude back to where the artifact is, where the particle is when we have a certain artifact in a certain way. So the most important effects in these artifacts are spatial misregistration of the MRI and intravoxel dephasing, so that means loss of signal. And the most important parameters, considering the sequences of the MRI, echo type, echo time, receiver bandwidth, field strength. There are a lot of other parameters, but these are the most important for this. So we simulate it using, we solve the Bloch equations in a voxel grid. That means the relaxation of the spins. And we use as input, of course, geometry, resolution of the grid, then a relaxation time matrix, material depending, the magnetic field around the object, then sequence parameters like echo time, repetition time, and so on, receiver bandwidth, then the strength and orientation of the external magnetic field, flip angle, and the number of subvoxels for dephasing simulation. So one thing what we first simulated was the magnetic field around these nanobots. So here we have one small ferromagnetic particle, and we simulate in different orientations the magnetic field around it, and we use that as input for the image generation simulation. And in order to verify it, we did experiments on magnetic particles embedded in agar in PE bottles. So here we see the MRI imaging artifact of a 2 millimeter steel sphere in a big agar block. And as you can see, the artifact spans much further than the size of the particle would like be.